Hey everybody, so we are into chapter 11, which is intermolecular forces in liquids. We won't be focusing so much on the liquids, but we will be focusing a lot on intermolecular forces. There's not really any math involved in this, really there's no math at all. It's just the conceptualness of intermolecular forces. They are the reasons why things are solids at room temperature, liquids, and gases. Right? They're the reason why boiling points are so high or freezing points are so low. They're really, really important to get a firm grasp of. They also help you explain all these things that happen in our universe. So our objective today is to be able to identify the strongest intermolecular forces and be able to explain why some things have stronger melting points or stronger freezing points than other compounds. So intermolecular forces, what are they? We talked a little bit about this last year. Bonds in between molecules, right? Like water, I drew this linear, but you know it as a bent molecule. But intramolecular forces are these bonds. Okay, those are known as intramolecular forces. But intermolecular forces are forces that happen between molecules, so in between more than one water molecule. So if we have water molecules together, it is the forces in between those water molecules. Okay? So a lot of times you'll see those intermolecular forces represented as dash marks. So make sure that you are able to see where these intermolecular forces are happening. Why does this happen? Okay, it all has to do with those dipole moments, those misdistribution of electrons. Let's talk about a more simpler form of intermolecular forces to help us visualize this. So say we have something like, let's go with HCl. Okay, HCl shares two electrons. They're bonding H and Cl together. They share two electrons. But which one is more electronegative, H or Cl? We should be able to know that Cl is a lot more electronegative than H is. Cl, that way, is going to have those electrons pulled really close to it. So those two bonds two electrons that it shares are going to be a lot closer to that chlorine than that hydrogen. Okay, that creates a dipole moment, kind of a tiny charge in between those two. Hydrogen becomes partially positive and chlorine becomes partially negative. Okay, that little fish looking thing is the symbol for partially in our chemistry world. Okay, so this is partially positive, partially negative. That's because those electrons are getting a lot closer. Even though they're shared, since chlorine is such an electron hog, it is wanting those electrons a lot closer. Well, that's not the only HCl molecule that's doing it. All of them are doing it. So what happens is that you get these nice partially negative and partially positive compounds going on, and what they do is they form these intermolecular bonds and get really close together. The stronger the intermolecular bond, the more likely it is to be a solid. All right? So let's talk about our four types of intermolecular forces. The first one is ionic. Right? We should know what ionic intermolecular forces are. These are like our metal and nonmetals. Things like NaCl. Right? NaCl. These are our strongest types of intermolecular forces. And the state that these guys take on at room temperature is usually solid. Right? Usually a solid state. And the cool thing about these is that these guys form these cool little structures. Okay? When we look at sodium and chlorine, sodium is positive, chlorine is negative because they actually give up all the electrons. Well, when they react with other salts, they end up forming this cool little crystalline structure, which is usually what we observe under a microscope. Okay, so this is like an ionic solid lattice structure is what they call it. And they get really close because those partial charges are so strong in between those sodium and those chlorines. So these are things like magnesium oxide. These are things like aluminum oxide, which is rust, you know that as a solid. Sodium chloride, that's a solid. Silver nitrate, which is a solid. All of these ionic compounds are typically a solid because of those strong intermolecular forces. The next one that we're going to talk about is called hydrogen bonding. Okay, and that is when hydrogen is bonded to N, an O, or an F. Okay, it's only N, O, and F because those have such a great difference in electronegativity. Those electrons get pulled really close to N, O, and F because there's such a difference in electronegativity there. Once you start getting to carbon and boron, there's not enough of electronegativity difference to create that really strong dipole moment that creates a strong attraction between molecules. The best example of this is one I showed you earlier, which was H2O. Right? That's how we get this nice attraction between these H's and these O's. Okay, these are the second strongest. And usually these are liquids, as you would know. Water's a liquid, right? But it doesn't take too much to turn it into a solid. We get it just a little bit colder, just 0 degrees Celsius, and it starts to freeze. Okay, HF, which is hydrofluoric acid, is hydrogen bonded. Okay, that is also a liquid. Let's talk about our next one, which is dipole-dipole, which is just polar molecules. Okay? Now, ionic bonds and hydrogen bonds are polar, okay? But they're not just polar, okay? Ionic bonds are a bond between a metal and a non-metal. Hydrogen bonds is H bonded to a NO and F. Yes, they're all polar, but these are molecules that are strictly just polar. Ones that don't have that hydrogen bonding between NO and F, and ones that don't have that ionic bonding between a metal and a non-metal. A great example of this is HCl. Okay, yeah, there's some hydrogen bonding going on there, but not to the right molecule, not to the NO and F for it to classify as the intermolecular force of hydrogen bonding. But again, we do got some partially positive, just not as much as you get in that hydrogen bonding. And it forms this nice intermolecular force here, where we got some dashed bonding going on. Not strict type bonding, but just some dashed bonding. Okay? And this is our third strongest, or second weakest, however you want to say. And sometimes liquids, sometimes gases. Okay, HCl is an acid, it's a liquid, but it doesn't take too much to turn it into a gas. Okay, and there's plenty of polar gases out there at room temperature. And our last one, last but not least, are our London dispersion forces. Or LDFs. Okay, and these happen between nonpolar molecules. These happen between nonpolar molecules. LDFs are also known as van der Waals. Okay, but I don't hear that too often. It's usually always London dispersion forces, just because you could say LDF. But sometimes you might hear van der Waals. Same thing. Okay, so great examples of this are H2, N2, and O2. These are the weakest, and if you think of hydrogen and nitrogen and oxygen, what are they typically at room temperature? They are gases. And you might be wondering, okay, how do these even create some sort of dipole moment? Right? There's supposed to be no pole whatsoever, so how is there any attraction between molecules? There's not much, but there is some. And how this happens is, say we got nitrogen over here. And we know that they got some electrons around them that they are sharing. Okay? Well, those electrons move around like bees around a beehive. Well, for a brief moment in time, what will happen is some of those B's will end up on one side, more populate on one side than the other. What this does is this creates just the tiniest dipole moment, a partially negative, partially positive side of a N2 molecule. Well, what happens to the other N2 molecules around that? Well, they start to react to that nitrogen gas molecule, and those electrons get the heck away from that side in this molecule and become partially negative and partially positive once more, and they form just the ever so slightest intermolecular force. That's why it's a gas. Okay, it's not very strong. That's why they're so spread out. So those are your 4 intermolecular forces. So let's do an example or two before I move on to the next thing. What about something like, let's go with NH3. Let's also go with CO2, and let's also do let's look at these. Okay? NH3, ionic hydrogen bonding, dipole-dipole, or LDF. NH3, that's definitely not ionic bonding. It's not metal to a nonmetal. Is a hydrogen bonding. H, is it bonded to a NO or F? It is. I know that when I draw this guy out, I got 3 H's bonded to an F. So this is definitely hydrogen bonding, or HB. CO2, I'm looking at that. Not ionically bonded. C and O are both nonmetals. There's not even a hydrogen in there to do hydrogen bonding. Is CO2 polar? Let me draw it, Lewis structure, just in case. I should kind of have it memorized already, right? That is definitely not polar. That's non-polar. So it's going to be LDF. HBr, ionic, nope. Is it hydrogen bonding? There is a hydrogen in it, and it's not to NO or F, it's to Br. Is it polar? It definitely is polar. Okay, so this is dipole, dipole. Okay, but so far, when I've asked you to list the strongest intermolecular force, I've just asked you to list the strongest, okay? There's actually a bunch of other different types of intermolecular forces going on here. And usually, it involves everything that is weaker than its strongest. So, if I'm looking at NH3, right, it's got hydrogen bonding, of course, but it's also got dipole-dipole going on in here. So it's also got some dipole-dipole intermolecular forces. Well, remember LDF when we were talking about that? It's just a misdistribution of electrons. Well, guess what? That happens in here too. Sometimes the electrons get shifted to one more side, and it does create an LDF type of intermolecular force. So typically what I'll ask you is, I will ask you what is the strongest intermolecular force in this compound. But every now and then I will ask you, list all of the intermolecular forces in a compound, okay? And usually it's all the weaker ones below it. Alright, so this one definitely has hydrogen bonding, it's its strongest. Well, it's also got that dipole-dipole, and it's also got that LDF. All hydrogen bondings will have that. Though, if the strongest is hydrogen bonding, it'll also have dipole-dipole and LDF. Everything has LDF. There's always going to be distribution of electrons due to those electrons buzzing around. But LDF, it's just got LDF. It doesn't got dipole-dipole. Okay? That's all it is. It doesn't have hydrogen bonding. It's just LDF. HBr. It's got dipole-dipole. Doesn't have hydrogen bonding though, but guess what else it has? It's got that LDF going for it. Okay, so everything always has LDF, whether it's ionic, hydrogen bonding, dipole-dipole. Okay, they all have LDF, but ones that are just LTF don't have dipole-dipole. They don't have hydrogen bonding, and those that are just dipole-dipole don't have hydrogen bonding. They have LDF. Okay. Let's look at ionic real quick, just because I feel like I should mention that one. Ionic is kind of one on its own that you could think of, right? If we're thinking about NaCl, it is ionic, but it doesn't have hydrogen bonding, right? It is polar, so it's definitely got dipole-dipole. And it's got electrons, right? So it's got LDF as well. So just be aware of that when I'm asking you what are all the intermolecular forces in a compound, that you're listing all of them and not just the strongest. Okay? Let's talk about some weird phenomenon that we kind of see in compounds all the time, but we don't really realize it. Okay? A really weird phenomenon here is we got Cl2, we got Br2, and we got I2. Now you might look at these and you might say, these are all LDFs. Okay, so they should all be gases, right? Because that's a really weak intermolecular force. It's usually going to be a gas. But here's the thing. Chlorine is a gas. It's a poisonous gas, chlorine gas. Br2 is a liquid. It used to be used in refrigerants, and then we learned it was toxic, and then we put CFCs in there, and then we learned that was putting a hole in our ozone. So we just keep switching it until we destroy part of the Earth. Anyway, I digress. And I2, iodine, is a solid. Okay, solid. The iodine they put on you at the doctor, they dilute, but usually it's solid iodine. Why does this happen? They're all LDFs. It's really, really weak intermolecular forces, but for some reason there's strong enough intermolecular forces here to create a liquid, and really strong intermolecular forces there to create a solid. And the answer is, if you kind of look at the periodic table, you might be able to figure it out. It's because they're getting a lot more electrons. It's called, and pay attention to this because they love to hear you say this on the AP exam, it's called polarization of the electron cloud, okay? You have to know that. You have to be able to say polarization of the electron cloud, okay? So, what is that? Well, remember how I was kind of saying with the nitrogens, there's a little bit more B's on the side of the beehive, and it creates a partially minus charge and a partially positive charge. Okay, nitrogen doesn't have that many. In N2, there's only 14 electrons. But if you go to iodine, okay, it's got 106 electrons. So what happens is that when we get to those larger molecules that have all those electrons, like I2, it doesn't just become some extra bees on one side of the beehive, it becomes a whole freaking colony of bees on one side of the iodine. So we don't just get a nice partially positive dipole, we get a really freaking large partially negative charge, so strong that it's almost like ionic bonding, that it creates this really, really strong intermolecular force that actually turns it into a solid. So you will see that all the time. Alcohols, as they get more and more atoms attached to them, they become harder to boil. Methanol, which is just CH3OH, is easy to boil. It's got a really low boiling point. But as we get to things like CH3, CH2, CH2, CH2OH, which is butanol, it becomes even harder to boil or break down those intermolecular forces. Okay? So I've been saying things like boiling point. Let's talk about those, okay? Because those matter with intermolecular forces. If things have strong intermolecular forces, they're harder to break apart, they're harder to turn to liquids, and they're harder to turn to gas. Okay, so they will ask you questions on the AP exam like, which compound has the highest boiling point? Okay, the highest boiling point. Well, which one has the highest boiling point? It all depends on intermolecular forces. Remember, if we're boiling things, it's going from a liquid to a gas. Well, the stronger the intermolecular forces, the harder it is to make something boil. The more energy we have to put into it, the higher boiling point it's going to have. So if we're looking at something like N2, let's go HCl, and then let's go NaCl, right? We're looking at these intermolecular forces. This one's LDF, really weak. This one's dipole-dipole, and this one is ionic, okay? We go from weakest to strongest here. boiling point is going to be really low for this one because at room temperature, it's already a gas. I already boiled it. It doesn't take hardly any energy at all. So this has a really low boiling point. HCl, dipole, at room temperature, it's a liquid, right? But we got to put some energy into it to turn to gas. Not really that much. But ionic, okay, at room temperature, it is a solid. It takes tons of energy to turn sodium chloride salt into gaseous salt, okay? So the highest boiling point is going to be the one with the strongest intermolecular force. I also might ask, what's the lowest boiling point? Okay, it's the one that's easiest to turn to gas. So be aware of that. Be ready to do that thought experiment in your head. Another thing they will ask you is that they will ask you which compound has the highest vapor pressure. Vapor pressure. That's just exactly what it says. It's just pressure created from vapors. Pressure's created from gases. So, the easier something is to turn into a gas, the more pressure it's going to give off. So we got to look at which one is easiest to turn it into a gas. Which one has the weakest intermolecular force. So which one is going to give off the most gas pressure. Well, think about this. At room temperature, NaCl is a solid. It's not really giving off any vapor pressure because it's not turned into a gas. HCl, not giving off that much vapor pressure because it's not turning into much of a gas. But N2, it's got those really weak intermolecular forces, so it is already a gas, and it's really easy to turn to gas. It's really easy to excite those molecules, so it's got the highest vapor pressure. Okay? What about if we were looking at H2N2O2? Which one would have the highest vapor pressure? Well, H2, okay? It doesn't have that many electrons. It can't be polarized. Also, it's really small. It's going to be bouncing into the side of those containers a lot more and creating that pressure. So the highest vapor pressure is going to be H2 in that case of those three. O2, it's got too much polarization of the electron cloud. It's going to have a little bit more of a dipole moment going on. Okay? And another thing they will ask you, and this is where, once again, you got to be ready. I could switch up the letters too. I could say lowest vapor pressure. But which compound has the lowest freezing point? And let's go back to our N2, HCl, and NaCl, which we know have LDF, dipole, and ionic. Okay? Which compound has the lowest freezing point? Think about that. Low. Low is cold with temperature. Which one has the lowest freezing point? Which one takes the lowest temperature in order to freeze? Well, NaCl is a solid, right? It's ionic. It doesn't take a whole lot to freeze it because it's even a solid at room temperature. Those intermolecular forces are strong. HCl is a liquid. Yeah, we got to slow it down a little bit more. We got to take that heat away in order for those guys to get real close in order to freeze. But N2, it's a gas. They're moving all over the place. We really got to slow down that N2. We got to go ahead and freeze it so much and make it ridiculously cold in order to get those molecules to slow down and attract to one another and solidify into a solid, okay? I mean, think of liquid nitrogen. We got to get it really cold just to turn it into a liquid. Okay, so be ready for things like that. One more thing I want to say. It's just, you might hear something called voltality, okay? Which is just how unstable a molecule is. Okay? How easy is something to turn into a gas, right? If I spill water on the table with hydrogen bonding, it takes a while for it to evaporate. It kind of has a low voltality. But if I put something like alcohol on the table, it evaporates really quickly. Okay, it's got a very high voltality. So things that evaporate quickly have high voltality. So we're thinking things with low intermolecular forces, things like gases, things that evaporate quickly. Things that have low voltality are things that don't evaporate or break apart quickly. Things like ionics, bonded solids, or things with hydrogen bonding like water. Okay? So that is that. Also remember, okay, I cannot say this enough. Likes dissolve likes. Okay? Polar things dissolve polar things. Non-polar things dissolve non-polar things. Be aware of that, right? The reason why water doesn't melt your skin off is because you got all these oils on your skin, okay, that are non-polar. If they were polar, water would melt your skin right off. So remember that. And one more thing that I want to say is I want to talk about this guy right here, which is not a weird clampy thing. It is a phase diagram. Okay? A phase diagram. What is a phase diagram? Well, it helps us relate, it just gives us a graph that helps us relate pressure and temperature. Okay? Now this is, say this is the phase diagram for water, okay? If we have a high pressure and a low temperature, what state do you think water is going to be in? The temperature is low, the pressure is high, that means we're pushing those molecules together, we're taking away that heat. It's going to be a solid. Okay? It is going to be a solid. What if we have something that has a really high temp and a low pressure, right? Low pressure, high temperature, that's going to be a gas. Things are going to be moving real fast. And then if you could guess here in the middle, kind of a balance between pressure and temperature is going to be liquid. Okay, it's good to know these, all right? It's good to understand what part of the diagram is what. One thing to note is this guy right here is our triple point. It's where all three states of matter exist at the same time. Cyclohexane, it's really easy. If you start heating it up and put it in a vacuum, you can see it transition from solid liquid to gas really quickly. And there's one other thing up here, which is called the critical point, which the critical point is just when it's hard to distinguish between liquid and gas. Okay, so this is hard to distinguish between liquid and gas. Okay, so that's a phase diagram. Make sure you know those parts. I'm sorry this went long today, but please understand that conceptually, understand that polarization of the electron cloud, all your intermolecular forces, and please have yourselves a great day.